So we were looking at the first order terms in the S matrix expansion, and today we're going to look at some higher order terms and discuss the general properties of the expansion in terms of Feynman diagrams. So just to remind you where we were. So we have our incoming state, t is minus infinity, the some initial state. And in the interaction picture, state evolves according to the Schrödinger equation with the interaction Hamiltonian. And these equations are equivalent to the following integral equation. T dt1 h hat evaluated at t1 phi t1. So notice that the time-dependent state appears under the integral sign as well. This is not an expression, this is an integral equation. But what we did is we started an iteration is you plug in. So treating this as small, the Hamiltonian interaction as small, you can put a trial solution, just assuming that the state is unchanged, it's just equal to the initial value. Put this in here, and we obtain the first order to first order plus minus I so now we have an expression for this state to first order, and this is what we were working with. This was so our first order S matrix operator is just this quantity here. But now what you can do, you can continue the iteration. You can say, now let's take this expression. This is the evolving state to first order. And you can plug it in to here. And you obtain the state to second order. Obtain the second order, you can then plug it back into here again and get the state to third order, and so on. So this is an iteration. And what do you get? You get the following series. So you have I plus minus I minus infinity t dt1 h hat I t1 initial state. That's the first order term. The second order term looks like this: minus infinity to t. And you might want to go through this. You may well have seen this before. It's just a general property of the interaction picture with a small perturbation. Done time-dependent perturbation theory in standard quantum mechanics, you will have seen this. It's exactly the same thing. Okay, so you should have seen this before anyway. Interaction T1, H interaction T2. this is going to second order. And let me just actually write this differently. Let me write this like this, plus dot, 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 going on and on. All right, so what we have is we can write the, anyway, the structure of the terms, it goes like this. There's an integral from minus infinity to the previous time. Anyway, let me write out the full, the general full series for S. So notice there's an I everywhere here, so factoring out the I, of course we define phi at infinity. So the S matrix operator is defined like this. We'll let t goes to infinity. So we're calculating the state that t is plus infinity. And the S matrix operator acts on the initial state to give you that state at t is plus infinity. So what do we get from this iterative expansion? The result looks like this. It can be written as a sum from n is 0 to infinity. What does the nth term look like? The nth term is minus I to the n, integral from minus infinity to infinity dt1, integral from minus infinity to t1 dt2, integral minus infinity to tn minus 1 dtn. So if you've not seen something like this before, you might want to check it through. So the nth term looks like this. Notice there are product of the you have the interaction Hamiltonian evaluated at n times as a product. And then you have these integrals with these funny limits. You integrate up to the time that comes next in the integration. Blah, blah. Should have seen something like this before. If you haven't, this is just standard perturbation iteration with a small perturbation. So we're solving the Schrödinger equation iteratively with this initial condition, treating this as a small perturbation. This is the result. Okay, now there's something that maybe you haven't seen before. Is this can be written as, it's a bit fiddly, it's awkward having these different limits on the integrals. There we don't want these different limits on the integrals. So it's actually possible to, with a little bit of fiddling, to show the following. That let's see, where am I? N minus I to the n. Over n factorial times the integral minus infinity. Now, all the integrals are from minus infinity to infinity. So what we've done is we've replaced the limit, all the integrals now have limits going from minus infinity to infinity. There's a 1 over n factorial in front here, and the clever part is this product of Hamiltonians is replaced by the time-ordered product. Now, what is going on here? So remember, the time-ordered product is, so we looked at it for two factors, but the time-ordered product, so what does it do? So basically, time running, write it like this, time running from right to left, or i.e., so what do I mean? What I mean is, if here we've got some product of factors, you know, if T2 is bigger than T1, then we have to swap these around and put this to the left. Okay, so basically, this time-ordered product is just a command that says, okay, you look at this product, and you look at the times, and you rearrange the terms so that the time is ordered, so the time is increasing from right to left. Okay, so the terms with T that's bigger go to the left. Yeah, okay, it's just a simple, that's all you do. So it's called the time-ordered product. All right, so now, what you can do, and also in the time-ordered product, and when you rearrange, you treat boson operators as commuting and fermion operators as anti-commuting. So what does that mean? When you rearrange these terms, if you swap two fermion operators, you introduce a minus sign. Now, it turns out, remember that the interaction Hamiltonian here is an integral over all space. How do we got it written here? Minus E psi bar A slash psi. Remember, there's a psi bar A and psi in interaction Hamiltonian. There are two fermion operators. So what does that mean? It means that whenever you swap any of these two terms, you're swapping two fermion operators. So for each fermion operator, you get a minus sign. So actually, there's no minus sign. Okay, and it turns out that actually this equality is true, provided you have this sort of form where the if there's an even number of fermion factors in the interaction Hamiltonian. Okay, so that when you do the swap, when you swap two of these terms, actually there's no minus sign introduced. Now, if you want to check this and say, hang on, well, what is going on? What you can check, it's probably a good idea to do a homework. So this is actually true. This equality, this equal sign here, is true term by term. Okay, so the term for, say, n is 3 here is equal to the term for n is 3 here. All right, it's true term by term. It's not just that the whole series is equal, but each term. So what you might want to do is, just to make sure if you're worried about this, check the case n is 2. So in other words, what you would be doing is checking that minus I squared, this double integral, minus infinity to infinity, and n is 2. dt1 integral minus infinity t1 dt2 of h hat t1 h hat t2. Check that that is actually equal to, running out of space here, minus I squared over 2 factorial times the integral times the time-ordered product of h hat t1 h hat t2. Sorry, it's all squashed there, but anyway, you see what I mean. Okay, you might want to just check this. So what you can do, it's not too difficult. If you look at this, what you'll do is break up this integral and think about, okay, what are the times when t1 is less than t2? What are the, so that this is the correct order. Sorry, if t1 is less than t2, then you have to swap these. Whereas if you look at the time where t1 is bigger, then that's the correct order. And if you look at this integral and a bit of change of variables, you should be able to see that these are actually the same. Okay, so we've got, by this trick, we've got rid of the changing limits on the integrals. And now finally, of course, because the interaction Hamiltonian can be written as an integral over all space of the Hamiltonian density, we can write this in a nice in the following form, which is really the final result. N is 0 to infinity minus I to the n over n factorial. We're integrating x1, x2. So we're integrating over the whole of space-time in each integral. And we have the time-ordered product of the interaction Hamiltonian at x1, sorry, interaction Hamiltonian density at x1 and x2, interaction Hamiltonian density at xn. This is the Dyson expansion. The Dyson expansion of the S matrix operator. Okay, so now all right, now I want to give you an idea of how, from this expansion, so I told you that if you study the terms, so if you study the terms that come from this expansion, terms in S matrix elements can be summarized, or sorry, can be represented by Feynman diagrams and the values of these S matrix elements, which which were proportional to something called the Feynman amplitude, can be given by a set of simple rules. Feynman rules. And I've mentioned to you that historically Feynman derived the rules before people derived them from quantum field theory. Feynman had come up with these rules and showed that they worked, they gave the right answers. He had no quantum field theory, he just had a picture, this intuitive picture based on the diagrams that he was drawing, which initially people thought is all a bit strange and what on earth does this mean? But it worked. And so soon, that was in 1949, soon after, in the early 50s, Dyson and Wick and Schwinger, Tominaga, various people worked on and saying, well, hang on, there must be a way to derive these rules from quantum field theory. This is the way they did it. So the starting point was this form of the expansion. And then there's something called Wicks Theorem, which I'm not going to go through it in detail because it's one of those things that is actually, it's not very intuitive. It's sort of weird, a lot of algebraic fiddling. And in the end, the result of Wicks Theorem, the implication of Wicks Theorem is this here. So, to go from here to here is through Wicks Theorem. And what tends to happen is if you're interested, you read Wicks Theorem once in your life and then you forget all about it because this is the result which you then use. But let me just give you a sense of what Wicks Theorem is. Wicks Theorem is simply this, that you can write the time-ordered product So here we're looking at the this is the time-ordered product that appears in the nth order term. So this S, probably a good idea to write this here. This is 1 plus S hat 1 plus S hat 2 plus S hat 3. Okay, I have a series of terms. The first term is just the identity operator. The second term is just one term here in the time-ordered product. The interaction Hamiltonian appears once. Okay, when n is 1, there's just the interaction Hamiltonian appears once. When n is 2, the interaction Hamiltonian appears twice. Okay, the nth term here, that interaction Hamiltonian appears n times. Now, if you look at the nth term, okay, there is this time-ordered product here. Wicks theorem is an algebraic result which shows that you can write this as a sum of terms where each term is a normal product So each term is a normal product with a coefficient involving factors EF and or, in other words, the Feynman propagators for the photons, or for the electrons, and or for the bosons, or for the fermions. So this thing can be expanded as a sum of terms. Each term is a normal product, and there are coefficients that involve these Feynman propagators. You remember that the Feynman propagators were defined as time-ordered products of two field operators. So this is where it comes from. From expanding this into a sum of normal products, you find that some of the coefficients can be factored out are time-ordered products of pairs of field operators, and that's where these Feynman things appear. If you're interested, you can look in the book and read through the proof. But the important part, you say, well, why does this help us? So the reason this is a clever thing to do is because if each term is a normal product, remember what a normal product so each normal product term, let's think about what it means if it's written as a normal product. So all the annihilation operators, and here I don't just mean for the photon, I mean the C's as well, I mean and the D's, annihilation, all annihilation operators in general act first. All of the creation operators act last. So what does this mean? So, i.e., if you look at when you look at the matrix element to go from the initial to the final state, all of the A's are appearing. Let me put it A's, there are C's, there are D's. Okay, just symbolically act first. And the creation operators act last. So when this is written in this form, what this does, this corresponds to a particular transition. Because there's a certain, for this to be non-zero, the state has to contain all the quantities that are annihilated here. Okay, if they're otherwise, okay, and then these terms have to create exactly the particles that appear in the final state. Okay, so you might want to think about that. But for this to be non-zero, this has to annihilate precisely all the excitations that are in here, and these have to create precisely all the excitations that are in there. Otherwise, the thing will be zero. Okay. So that is the point of why write this as a sum of normal products? Is because otherwise, what can happen if you don't have normal products? You can get a term that creates, imagine if here you had a C dagger, you could create a state, and then there could be a C that annihilates the state, and it just makes things more complicated to work out what it corresponds to. There'd be nothing wrong with that, you can still work out the matrix element. The point is, by Wicks Theorem, by expanding this in terms of normal products, each term in this series, it's now clear, this corresponds to a particular transition. And I'm going to show you an example. We're going to look at an example of one of these. We're going to look at an example of one of these terms to see exactly what it looks like. But this is the general gist. This is the point of expanding it in normal products. Maybe it'll be clear when I show you a particular example. We're going to look at a particular second-order term corresponding to Compton scattering. In other words, I'm going to show you what one of these terms in the Wick expansion actually looks like. So this is often called the Wick expansion. The Wick expansion. Okay. So sounds a bit vague, it's because it is, but if you're interested in looking at the details, you can look at the book. But I'm going to show you an example of one of these terms, so then it probably should become clearer to you what the point is. Okay, so we're moving forward. So now, now the result of Wicks' theorem is that so here I've written it like this, that the terms in the S matrix elements can be represented by Feynman diagrams, and the values can be given by a set of simple rules. More specifically, the relevant Feynman diagrams, I've mentioned this already, can be built up by from combinations of basic vertices, by which I mean this kind of thing, etc., with factors IDF and ISF for what are called internal lines. So, for example, if I have a Feynman diagram like this, where I've joined two basic vertices, the internal line gives you a factor IDF. Where does this come from? From the point of view of the Wick expansion, when I look at one of these terms that's a normal product that corresponds to a particular transition, it will correspond to a particular diagram. So this Feynman diagram, for instance, this could be electron-electron scattering. There is a particular second-order term in the Wick expansion. It's a particular normal product, which corresponds to this transition. This is a transition where I have two electrons of momentum, let's say P1 and P2, and the final momentum is P1 prime, P2 prime. If I look at this transition, P1, P2 goes into P1 prime, P2 prime. So I have, this is my initial state, this is my final state. Okay, the initial state is two electrons with these momenta, final state is two electrons with these other momenta. There is a particular term, when you look at the Wick expansion, there's a particular term, a normal product, that corresponds to that transition, in the sense that in the normal product, there are the annihilation operators that will annihilate these two states, and there are the creation operators that will create these two states. So there's that one term that appears, this big messy expansion, there's one term that contains exactly the right factors to annihilate these and to create these, okay? In addition, when you look at that term, you find that there is a coefficient involving the Feynman propagator. So this term is proportional to the Feynman amplitude is proportional. There's a factor involving the Feynman propagator that appears in the Feynman amplitude. And the way we describe this symbolically with the Feynman rules, which we're going to go into, is you say that, well, you can summarize all this by saying, well, when there's an internal line, this is an internal line, or an internal photon line, is associated with a factor given by I times the Feynman photon propagator. Just give you a sort of sense of roughly how this expansion, how you derive the Feynman rules from this expansion. Okay, so now let's go in a bit more detail. Let's go back to, try to do it this way around. I was going to do it this way around, but actually, I think it'd be better to do it this way around. Let's look now at one of these terms. Otherwise, it all sounds a bit too hand-waving. Let's look at one of these terms. So let's look at an example. So imagine you're looking at the Dyson series and the Wicks expansion of each of these terms. Where from the Wicks expansion, the time-ordered product, let's say you're going to second order. Let's say you're looking at second order. So, okay, let's say you carry out the Wicks expansion of this time-ordered product at second order. So, what you find is one of the terms, the S matrix operator to second order contains contains various terms, which we're going to look at. If you're interested, okay, let me write down just symbolically. So remember, the second order term in the S matrix operator is given by a double integral over all of space-time times this time-ordered product from the Dyson expansion. And then time-ordered product is a sum of normal products. So what do I get? I get a sum of integrals over normal products. So to second order, the S matrix operator, you get a whole lot of different terms corresponding to various processes to second order. We're going to concentrate on this one. So first term here is given by, if you want the reference in the book, it's equation 710A. And this is what it looks like. So I'm going to show you an example. We said that the Wicks Theorem, you expand this as a sum of normal products. Here's an example of what comes out. Remember, of course, that S hat 2 is equal to, just so you're clear of what we're doing here, S hat 2 is minus I squared over 2 factorial double integral times the time-ordered product x1, oops. Okay, so what we're doing is we're looking at the second order S matrix operator and time-ordered product here for two factors is expanded into normal products by Wicks Theorem, and one of the terms that you get looks like this. So there is psi bar hat minus x1 gamma alpha I s Feynman x1 minus x2 times, this is all under the integral sign, a hat minus alpha x1 a hat. So these pluses and minuses are the positive and negative frequency parts. So this minus e squared is just, well, the minus I squared gives you a minus. Remember, in the interaction Hamiltonian, there's an e psi bar a slash psi. Okay, so two of these factors, two of the, I get the sign wrong. I should know by now, but there you go. Minus. Anyway, it doesn't matter. If I've got two of these factors, so for each of these factors, there is a factor E, which is electron charge. So two of these factors, I get an E squared. Okay, so here this gives me a minus. Here I've got minus E squared, so it's E squared. I have minus E squared. And the factor 2 has gone away by, so it's cancelled off somewhere. Here, the time-ordered product has been expanded by Wicks Theorem into a sum of normal products. One of those terms is this thing here. This thing here. Now remember I said it's a normal product and with coefficients involving Feynman propagator. Here you see indeed the Feynman propagator is in here. The rest of it is a normal product. Remember, the positive frequency parts contain annihilation operators. The negative frequency parts contain creation operators. So you see that here this contains annihilation operators, and then creation operators and creation operators. So the ordering, it is indeed a normal product. The annihilation operators are all to the right, and the creation operators are all to the left. So this quantity under the integral sign is one of these normal products from the Wick expansion. Okay, now this process, so this should correspond to a particular physical process, okay, because it's a normal product. So from this argument that I told you, it corresponds to a particular transition. Which transition does it correspond to? Well, let's think. Let's have a look. We have if we look at the structure here, we have going from left to right. So here we have, so this should be, we should have a C dagger, A dagger, C, or the order here doesn't matter, but let's write it like this. So this negative frequency part contains annihilation operators. There's an annihilation operator for an electron. Okay, this contains annihilation operators for electrons. This contains annihilation operators for photons. This is a negative frequency part, contains creation operators for photons. And finally, this negative frequency part contains creation operators for electrons. Go back and check your expansion of the Dirac field. So, what kind of process, for this to be non-zero, what kind of process do we have to have? Well, we're going to have to annihilate an electron. Got an electron coming in, you've got a photon coming in. Just draw it like this. Okay, the initial state has to contain an electron and a photon, because we annihilate an electron and a photon. And the final state has to contain a photon and an electron. Okay, so this corresponds to a process where you have an electron and a photon coming in, and an electron and a photon coming out. In other words, it's Compton scattering. So, have a photon, electron, photon, electron. This is Compton scattering. Photons scattering, photon and electron that are scattering off each other. Now, I might mention to you, remember I said there's this whole series of terms here. The next term here, B, actually corresponds to also corresponds to Compton scattering, but where, hang on, I need more room to write this. Corresponds to the following diagram. Where so here the electron comes in, it absorbs the incoming photon, and then it emits the outgoing photon. Here what happens is that first the photon emits the outgoing photon, then it absorbs the incoming photon. And from the point of view of the operators, what you'll find is there's just another term where these A and the A daggers are swapped around, where you are there's just a different term with a different ordering of these operators, so the initial first the outgoing photon is created and the incoming photon is annihilated. Anyway, so what happens, the actual amplitude for Compton scattering is the sum. You actually have to add up these two contributions to get the total amplitude for Compton scattering. Okay? Now what happens is, I'm trying to give you a sense of where these diagrams come from the expansion. Okay, from the perturbation expansion. But the fact is, once you've done this, once in your life, you forget about the expansion. In practice, once you know that, look, the upshot, what Dyson and Wicks did, the result is simply that once you've got the basic vertex, all the physical processes are obtained by combining these vertices. So nobody goes back and worries about, what does this look like, the various terms, people just draw these diagrams, say, right, let's just draw all possible diagrams and we can see what the possible processes are. So clearly, if I say to you, look, I've got an electron and a photon coming in, they're scattering, and the final state is electron and photon, what kind of Feynman diagrams could that correspond to? Well, here's one, here's another one. And they're both in the perturbation series, but you forget the perturbation series. It's all the information is in the diagrams. Okay, so now what we're going to do is I have a beautiful, sexy homework problem for you. All right, so the homework problem is to actually evaluate the matrix element of this term for this process. So what are we going to do? We are going to show that homework. So it's basically to show equations 734 to 738a. So what does this look like? 734. So what are these equations? Let me write them down. So we're looking at, you are being asked to evaluate the S matrix element for this particular term in the Dyson-Wick expansion, where the initial state, let me write down here, the initial state is equal to, so we're suppressing spin and polarization indices. So the initial state, so you act on the vacuum with your creation operators. The initial state contains, in other words, it's an electron with momentum p and the photon with momentum k. Your final state is equal to C dagger. The book uses P prime. Let's use P prime. K prime 0. In other words, it's an electron with momentum P prime and a photon with momentum K prime. So what we're looking at is the following process. We have an incoming photon of momentum K, incoming electron of momentum P, and we have an outgoing photon of momentum K prime, outgoing electron of momentum P prime. Notice there are we're suppressing the spin and polarization indices, just to save ourselves having to write down all those indices. Anyway, what you're required to show for those initial and final states, that the S matrix element, so you take those initial and final states and you calculate the matrix element of this operator with all of these beautiful field expansions in here. So you should find the following, minus E squared times, we have a double integral P4x1, P4x2. Let me see. Okay, the whole bunch of terms. So these terms are all under the integral sign. There is a square root of m over v e primed u bar p prime e to the I p prime dot x1. Okay, this should come from the psi bar. There's going to be the psi bar term. Remember, this is the negative frequency part, so it's a sum of terms. But one of those terms is going to give you this factor here, u bar. There's only one non-vanishing term in the matrix element, and it will give you this factor with a u bar. Then there will be a factor 1 over the square root 2v omega primed. Let's use the slash. The book uses, let's use the slash. Epsilon slash k prime. So that's the epsilon slash k prime is just gamma alpha epsilon k prime alpha. Okay, epsilon is a 4 vector polarization vector. So let's use the slash notation. Save as writing the gammas. Then we have e to the I. So this is clearly going to come from this term here. So there's an e to the I k prime dot x1. Then we have the Feynman propagator in here, which is written in terms of written in terms of position space, we can write this directly. We can rewrite this in terms of momentum space. Let's write the Feynman propagator as an integral over momentum space. Okay, this term I've just written down, this is just, all of this is just I s Feynman x1 minus x2. Okay, I've just written it as a four-dimensional Fourier transform. Then there is the factor, there's another factor coming. We have a 1 over the square root of 2phi omega. And there's an epsilon slash k e to the minus I k dot x2. And then finally, there's a factor square root of m over ve up e to the minus I p dot x2. Okay, this is what you should get. Right, you should get this matrix element, and as I said, the origin of this term, the expansion for this operator should give you the only non-zero contribution will give you this term, and then you've got the electromagnetic, the A hats, the minus and the plus should give you these two terms, and then this expansion here that just contains annihilation operators. This is annihilating the additional electron. The only non-zero term in the matrix element, you get the this is the contribution from the expansion of this here. So please go through and show that. And then, furthermore, so if you then do the integrals over x1 and x2, then, well, if you collecting up terms here, there's an ix1, you can collect up the x1 factors, there's a p prime plus a k prime minus a q, and there's also the term in x2, collecting up the terms in x2, there is a q minus a p minus a k. If you just look at the various exponentials there, and so what is this? This is just a delta function for p prime plus k prime minus q times a delta function for q minus p minus k, which can be written as, seeing as q, this is non-zero only when q is p plus k, so I may as well put q is p plus k in here. So this can be written as p prime plus k prime minus p minus k minus k. So if you think about this from the point of view of Feynman diagram, here we have, let's write it here. We have p prime in terms of 4 momentum, where P and P prime, K and K prime. And here the internal, from the point of view of the Feynman diagram, there's an internal momentum Q, which is associated with the Feynman propagator. Notice that what these delta functions are saying is, well, Q is equal to P plus K. So diagrammatically, the form momentum is conserved at each vertex. Form momentum conserved at each vertex. Even though NB Q squared is not equal to M squared. Remember, a single vertex by itself cannot satisfy energy momentum conservation. We have K squared is 0. This is a physical photon coming in. We have P squared is M squared. This is a physical electron coming in. This internal is often called a virtual electron. The form momentum Q, if I take the sum of P plus K, where P is a physical momentum, M with P squared is M squared, and K is a physical photon momentum whose square is 0, it follows by the kind of manipulation I showed you last time that Q squared cannot equal M squared. Okay, it cannot be a physical momentum. So this is a virtual, what is often called a virtual electron. And the internal line represents a virtual electron. And the form momentum that appears in the Feynman propagator is this sort of virtual momentum, if you like. But anyway, form momentum formally conserved at each vertex, but this is not a physical momentum. Not a physical momentum. It's often called a virtual momentum. Okay, carrying on. And of course we have overall, and of course the overall, the sum of the final momenta is equal to the sum of the initial momenta. Okay, so overall energy momentum is conserved. P plus K is equal to P prime plus K prime. That comes out of the matrix element. But now what we want to do is write this in a final form. So just take 5 minutes. And so what you do, so what you've done, you do your homework problem, you do this, you do these integrations, you convert these to delta functions, and then you should integrate over Q so at this point, so carry out the integral over Q, and you should find the following form. So this is still your homework problem. Find the following form. You should find 2 pi to the 4 times the overall delta function that conserves energy and momentum. Okay, so I've got the sum of the final momentum minus the sum of the initial momentum. Then there is a factor m over VE. There's a factor root m over VE, then there's root m over VE primed, and we have 1 over the square root of 2V omega, and 1 over the square root of 2V omega prime, and then we have something called the Feynman amplitude, which this is associated with this particular diagram. That's why it's got the label A. Remember, there's another diagram that we were worried about where. So this is called the Feynman amplitude. MA. So I'm going to write it slightly differently from the way the book writes it, because It's more the way you would write it down from the Feynman rules. This is what you should get. U bar P prime. Remember the spin indices are suppressed. Spin and polarization indices are suppressed. Notice we have polarization 4 vectors. Epsilon mu kr, which if you lower the index, you can write it as epsilon kr mu, or simply epsilon k, sorry, these are 4 vectors, epsilon k mu. I think I wrote the mu and the k the other way around last time. I think it makes a bit more sense to write it like this. But anyway, just as notation, remember also NB, the scattering cross-section for this process, I should have mentioned this already, I think I did, is proportional to the modulus squared of the S matrix element, so it's proportional to the modulus squared of the Feynman amplitude. But let's just look at the structure of this term. Let's look at the Feynman diagram. Next time we're going to write down on Thursday, we're going to start writing down Feynman rules, which summarize the results of all of these calculations. Okay, so let's just look. If you were going to look at this from the point of view of the Feynman rules, you wouldn't do this calculation. Forget this S matrix element. You just draw this diagram. I say I've got an electron, a photon, photons absorbed, the photons emitted. What is the Feynman amplitude corresponding to this process? The rule that you write down is you follow the arrow on the fermion line and you start writing from right to left. And the first rule, one of the Feynman rules, says, okay, if there's an incoming electron, you write down a factor U. You've got an incoming photon, you write down a factor epsilon. You then hit a vertex. When you hit a vertex, you write down a factor IE gamma. Then there's an internal electron line. So here you've got IE. Here you've got an internal electron line. You write down a factor I Feynman propagator with the corresponding 4 momentum. Sorry, where I should write here the Q. Q in here is fixed at P plus K. It's not an extra variable. Q is equal to P plus K. In fact, you could just write it directly. Instead of IS Feynman of Q, you could just, maybe it's safer, better to just write IS Feynman of P plus K. Okay. Anyway, you hit the internal line, you write down the factor ISF. You then hit another vertex. You write down the factor IE gamma. Then there's an emitted photon, another factor epsilon, with of course the corresponding final momentum. Then there's a final electron. When there's a final electron, you write down the factor U bar with the appropriate momentum. And that's the Feynman amplitude. Note that this is a complex number. This is a complex number. So here I've got a 4-component column vector. Here I've got numbers summed over nu. Here there's a 4x4 matrix. Here there's a 4x4 matrix. 4x4 matrix, numbers, row vectors. The whole thing gives you a complex number. That's the Feynman amplitude. So please go through this homework so you see the mechanics of where all this comes from. This is how one of the terms in the Dyson-Wick expansion corresponds to this particular process, and the matrix element for that process takes this form. We're going to see this form is generic. In any process, in any S matrix element, there's an overall delta function for energy and momentum. These factors, when you have, here you have what are called external electron lines. For each external electron line, there's a factor, so root m over v, root m over ve, with the corresponding energies, E's and E's primes. When you have external photon lines, you have factors 1 over root 2 v omega. So for each external particle, you have these factors, and then there's the Feynman amplitude. So the Feynman rules tell you how to write down the amplitude. For each external particle, you have these factors. There's the overall delta function. That's the general expression for the S matrix element of any process. So please do the homework, and then on Thursday, we're going to write down Feynman rules and summarize all possible processes that one could be interested in. And if there are any questions, please see me after class. I'll be in the corridor. And if you have any problems, worries, getting lost, please email me for an office hour. Okay, see you on Thursday.